Welcome back to Honors Calculus. In this video, we're continuing our discussion of Lesson 1 on inequalities with an idea on ordering relations. Ordering relations is the broad idea that is more specifically inequality, or inequality is a specific example of an ordering relation. And ordering relations are important because you'll remember from the last video that the real numbers are defined as an ordered field, a field that has an ordering relation. So, with these ideas in mind, let me get my head out of the way and we'll dive in and start looking at some of these ideas of orderings. To talk about an ordering relation, we need to form a subset of the real numbers that we're going to call the positive real numbers. And we're going to define the positive real numbers based on two properties. First of all, the natural numbers that we have already defined as being positive numbers must all be positive real numbers. And second of all, we have this three-piece discussion. If you take any real number, A, then exactly one of these properties must be true, and the other two are going to be false. Either that number is a positive real number, which means that its opposite is not a positive real number, and it is not zero. Or the opposite of A is a real number, which means that A itself is not a real number and A is not zero. Or A is zero, in which case A is not a positive real number, and the opposite of zero, which is also zero, is still not a positive real number. So we can divide off the positive real numbers, and we can also get the negative real numbers and zero as three separate sets, but the positive real numbers are the only ones we're really going to worry about. Right? That gives us something to work with. We're getting to where we want to be. The last thing is that the positive real numbers are still closed. So if you add two positive numbers together, the result is positive. If you multiply two positive numbers together, the result is positive. It's a nice definition of positive numbers. Again, kind of backwards of what you have seen in the past, backwards of what you are accustomed to. We are looking now at starting with this definition, these properties, as the definition of the positive numbers. And in previous coursework, you've defined positive numbers kind of intuitively. The positive numbers are the ones that are on the right on the number line, and the negative numbers are the ones on the left, and tried to go from there. Right? That's really nice when you are dealing with relatively simple numbers. Right? Integers, even fractions, are pretty easy to work with in that regard. But if we don't want to have to know anything about the numerical value, we need something a little bit more abstract, and that's why we are using this tool today. All right, but we now have this definition that gives us the positive real numbers, and with that, we are going to form the inequality relation. An ordering relation is any rule that is reflexive, symmetric, and transitive. Reflexive means that everything is related to itself. And I'm sorry, I'm a bit of an idiot here. I don't want to say symmetric, I want to say anti-symmetric. Symmetric is a property of equations. Anti-symmetric is a property of inequalities and other ordering relations. And the anti-symmetric property says that if you have inequality that works in both directions, that only can happen if you're comparing a number to itself. And the transitive property, make sure that actually is on the screen. If A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. You are probably already familiar with these three properties. They are useful tools in working with inequality. These are things that have probably come up in algebra coursework for you in the past, but we're kind of flipping the story and we're taking these as the definition of an ordering relation and trying to use that ordering relation to define inequality. So, here we go. We are going to define the meaning of A is less than B as A is less than B if and only if B minus A is a positive real number. And then we'll define A is less than or equal to B if and only if A is less than B or A is equal to B. And our claim is that this rule for less than and for less than or equals forms an ordering relation on the real numbers. And for something to form an ordering relation, that means it must be reflexive, symmetric, and transitive. So to prove that this definition, A is less than B if and only if B minus A is a positive real number, let's try to prove that that satisfies each of the three definitions. Right? The reflexive property is pretty easy. We know, by definition of equality, that A is equal to A. And since A is equal to A, then it must be the case that A is less than or equal to A, because that's how we defined less than or equal. The anti-symmetric property is where we can start getting things interesting. The anti-symmetric property tells us that if we have two real numbers A and B, where A is less than or equal to B and B is less than or equal to A, then A and B must be equal. Right? Since A is less than or equal to B, that means that either A is equal to B or B minus A is a positive real number. And since B is less than or equal to A, that means that either A is equal to B or A minus B is a positive real number. Right? But we will note here that A minus B is the opposite of B minus A. Opposite of, I asked you to prove, is the same thing as -1 times something, so we can think of this as distributing. The opposite of B minus A is the opposite of B minus the opposite of A, or the opposite of B plus A, which is how we define A minus B. So we know that exactly one of three claims can be the case. Exactly one of these three claims can be true. A minus B is a positive number, B minus A is a positive number, B minus A is 0. That's the definition of the positive numbers. Right? A and B are real numbers, so A minus B and B minus A are also real numbers, and so by the definition of the positive real numbers, exactly one of these three things can be true. And finally, we will note that A is equal to B if and only if B minus A is equal to 0. You can get that by subtracting A on both sides of the equation. All right. We know that A is less than or equal to B, which means that either, get myself back here so I can point. All right. We know that A is less than B, which means that either B minus A is a positive number or B minus A is 0. We also know, I shouldn't stand over here, I can't actually see the screen to know what I'm pointing at, I should stand over here. We know that B is less than A, which means that either A minus B is positive or B minus A is 0. So we need one of these two things, and we need one of these two things on the outside, and we can only have one total. Well, the only place where it lines up is if that third one is the 1. So that third one must be true. The other two must be the ones that are false. Let me run through that again. Because of the definition of the positive real numbers, one of the three statements, a minus b is a positive number, b minus a is a positive number, b minus a is 0, is true. Because we know that a is less than or equal to b, then either b minus a is positive or b minus a is 0. And because we know that b is less than or equal to a, either a minus b is positive or b minus a is 0. The only way we can satisfy both of those claims is when b minus a is 0. The other ones preclude satisfying. If b minus a is positive, then it cannot be the case that b is less than a. And if a minus b is positive, it cannot be the case that that a is less than or equal to b. So b minus a is the only way to satisfy that. So we get that a is equal to b. All right, now let's go on to the transitive property. Let's pick three real numbers, a, b, and c. Let's insist that a is less than or equal to b, and let's insist that b is less than or equal to c. The transitive property tells us we should be able to prove that a is less than or equal to c. Well, the only thing we know is that since a is less than or equal to b, that means that either a is equal to b or b minus a is positive. Since b is less than or equal to c, that means that either b is equal to c or c minus b is positive. If a is equal to b, then this is easy, because we can use a direct substitution, replace b with a in the second inequality, and we have our result. If b is equal to c, then this is easy, because we can replace b with c in the first inequality, and that will give us the result we are looking for. So the only really interesting case is the case where neither of the equalities hold. So let's take a look at c minus a. Once again, we are going to use mathematicians' favorite trick, inventing something that wasn't there before. Specifically, a minus b and a plus b. You cannot arbitrarily subtract b. You cannot arbitrarily add b. But if you both subtract and add b, then they cancel each other out, and you spent a lot of writing to do absolutely nothing, which is what mathematics is all about. I'm going to split that up and look at c minus b and b minus a separately. And I'm going to notice that c minus b is a positive real number, and that b minus a is a positive real number. And the positive real numbers are closed under addition. So if you have two positive real numbers and you add them together, you get a new positive real number. And since c minus a is a positive real number, that's the definition of inequality. We get that a is less than or equal to c. We proved the reflexive property, we proved the symmetric property, we proved the transitive property. Thus, we've proved the theorem. We have proven that this strange definition does in fact give us the inequality that we need to be able to talk about the real numbers. So now we have not just a field of real numbers, we have an ordered field of real numbers. We're 2/3 of the way to our definition of real numbers. And we'll get there. We'll get the rest of the way. But for right now, let's play around a little bit with this idea of an ordered field and see what we can do now that we have it. And what we're going to do, first of all, is something that you are very familiar with. The next thing we want to do is solve some inequalities using the standard properties of solving linear inequalities that you learned in a basic algebra course some time ago. If you have three real numbers and you know that a is less than b, then you can add c to both sides of the inequality and the inequality is still true. If c is a positive number, you can multiply both sides of the inequality by c and the inequality is still true. If c is a negative number, which means the opposite of c is a positive number, then you can multiply both sides of the inequality by c, and it flips the inequality. These are properties that you have used to solve inequalities for quite some time at this point. Once again, I'm using a strange definition of inequality. We need to make sure that this definition, putting us on a firm foothold, actually does the things that you expect it to do. So let's try to prove this. Let's name these three properties or number these three properties 1, 2, 3 so we can just work our way down the list. And looking at property 1, we have not much about inequalities. We know that if a is less than b, that means that b minus a is a positive real number. That's all we know. And we have our cute trick. We can add and subtract the same thing without changing anything at all. Right? B minus a is the same thing as b plus c minus c plus a. And we can group b plus c together. We can take out the negative distributive property. The negative of c plus a is the negative c plus the negative of a. And we can, of course, rearrange using the commutative property of addition. Right? B minus A is a positive number, and B minus A is the same thing as B plus C minus A plus C. So B plus C minus A plus C is also a positive real number, which means that A plus C is less than B plus C. There we go. We can use basically the same proof for showing that the multiplication works. I'm not going to go through the one for the positive numbers. Actually, I'm not going to go through it at all. I don't think it adds much of anything. It looks very similar to what we have here. I encourage you to take some time to try to write it out in detail, but I'm not going to assign that because I have other things I want to focus on. Specifically, we are not often going to see an inequality by itself in this course. What we're going to see a lot of are three-piece inequalities. So the inequality A is less than B is less than C is the same thing as A is less than B and B is less than C. And these are the things we're going to be working on. So if I have an inequality, something like -3 is less than or equal to 2x minus 7 is less than 3, then I should be able to solve this using the properties of inequalities that we are very accustomed to. This is two inequalities at once, but I can take the shorthand, and on the first inequality, I'll add 7 to both sides. And on the second inequality, I'll also add 7 to both sides, which is essentially adding 7 to all three sides of the three-piece inequality, giving me that 4 is less than or equal to 2x is less than 10. And then finally, divide by 2 on all three sides to get 2 is less than or equal to x is strictly less than 5. Right. Something that you should be very familiar with already, but we've now established a theoretical foundation for why you are able to do this, and we have a better definition of inequality, which is going to help us out later on. But before I wrap up, I would like to give you a similar inequality to solve on your own. I would like you to take a look at -5 is less than 7x plus 2 is less than or equal to 30. Just as a quick warm-up to make sure you remember how to solve three-piece inequalities, take a few minutes, write out the solution to that one, and I'll see you in the next video.